Picture this. You're standing on a shoreline, the gentle rush of waves lapping at your boots. But here's the twist. The water isn't water at all. It's liquid natural gas, a frigid alien cocktail of methane and ethane, chilling you to a bone-numbing minus 180 degrees Celsius. The air isn't crisp and clear, it's thick, hazy, and tinged with the photochemical smog that would make any Earth city blush. In every splash, every ripple in this bizarre hydrocarbon sea could be hiding chemistry we've quite literally never seen before. Welcome, my friends, to Titan, Saturn's largest and most enigmatic moon. It's a world where methane flows like water, carving rivers and filling vast lakes, and where those very lakes might just be brewing the raw, primordial ingredients of life itself. In the next few minutes, we're going to dive deep, figuratively, of course, because an actual dive would be complicated, into those alien seas. We'll explore what's actually down there, why some patches of liquid vanish overnight as if by magic, and how a plucky, nuclear-powered flying drone called Dragonfly might finally give us the answers to some of the universe's biggest questions. Could it tell us if we're truly alone in this cosmic neighborhood? Or if life, in some form, has found a way to thrive in conditions we once thought impossible? Get ready for a journey to a world that's both eerily familiar and profoundly strange. The twisted Earth. Titan, at first glance, feels uncannily familiar, a kind of dark mirror image of our own world. Rivers carve intricate valleys across its surface, clouds drift lazily overhead, and powerful seasonal storms periodically swell vast basins. But here's where the cosmic fun begins. You have to swap out almost every fundamental ingredient. Instead of life-giving water, imagine a world where liquid methane and ethane are the dominant fluids. Instead of solid rock, the bedrock beneath your feet is rock-hard water ice, so cold and compressed it behaves like granite. And instead of our comforting 24-hour day, prepare for a glacial 16 Earth day slog of light and dark, each cycle stretching on for what feels like an eternity. The result is a world that truly feels like Earth's estranged, slightly sinister twin. Same fundamental geological and meteorological processes, but built from an entirely different set of materials. And that difference, that fundamental swap of chemistry, is precisely what makes Titan's lakes so utterly bizarre and fascinating. On Earth, water's unique properties, like its ability to form strong hydrogen bonds, are fundamental to everything from our weather patterns to our biology. But on Titan, methane and ethane don't play by those rules. Their molecules interact through much weaker van der Waals forces. This means their mixtures refuse to behave predictably, leading to what scientists call non-ideal mixing. It's less like mixing water and juice and more like trying to combine oil and vinegar, except with far stranger consequences. Now throw nitrogen from the atmosphere into this already volatile mix, and you've got a three-way molecular tug-of-war. This chemical wrestling match can dramatically alter the density of the lake layers, sometimes flipping them upside down overnight. One moment, the top layer of a lake might be rich in lighter methane. The next, denser ethane might have sunk, causing methane to froth to the surface like a shaken soda bottle finally popping its top. This isn't just a theoretical oddity. It means a lake's composition and even its surface appearance can change drastically in a short period. Imagine waking up to find your local lake has completely reorganized itself. Scientists label this non-ideal mixing, but you, standing on that alien shoreline, might just call it pure, unadulterated alien chaos. Below about 84 Kelvin, that's minus 189 degrees Celsius, these lakes can stratify into distinct layers, with methane-rich, denser layers at the bottom and ethane-rich layers floating on top, separated by sharp compositional gradients. It's this dynamic, unpredictable behavior that makes studying Titan's lakes such a thrilling and challenging endeavor. A probe in the mist. For decades, Titan was little more than a fuzzy orange ball in our telescopes, shrouded in a thick, impenetrable haze that guarded its secrets closely. We knew none of this intricate chemistry, these strange dynamics, until a pivotal moment in 2005. That's when the European Space Agency's Huygens probe, a marvel of engineering, belly flopped through Titan's infamous orange veil. It was a plunge into the unknown, a blind dive through an atmosphere 4 times denser than Earth's, but with only a fraction of the gravity. For 2 exhilarating hours, as Huygens slowly descended, it relayed back precious data and images. We saw snaking channels etched into the landscape, clear evidence of flowing liquids, and vast, dark plains stretching into the distance. Finally, after its epic journey, Huygens settled softly into what appeared to be a floodplain, a landscape dotted with rounded pebbles. But these weren't ordinary pebbles. They were made of water ice, hardened to the consistency of rock by the extreme cold. The photos that streamed back were astonishingly familiar, looking uncannily like a muddy creek bed in, say, rural Tennessee. Except, of course, the mud was a viscous hydrocarbon goo, and the water that had sculpted these features had been gone for days, perhaps weeks, evaporated or seeped away. Huygens didn't actually land in a lake, as some had initially hoped. But its parent spacecraft, the Cassini orbiter, continued its tireless work, circling Saturn and making numerous flybys of Titan. Equipped with sophisticated radar, Cassini peered through the moon's hazy atmosphere, mapping its surface with unprecedented detail. And what it found was incredible. Thousands of lakes and seas, concentrated mostly near Titan's North Pole. These weren't just small puddles. They varied wildly in size. Some were puny cons, just a few kilometers across, barely a blip on the radar. Others, like the colossal Kraken Mare, sprawled wider than Earth's Caspian Sea, an alien ocean dwarfing terrestrial bodies of water. The smallest of these lakes often appeared mirror flat, reflecting the dim sunlight like polished obsidian. But the truly massive ones, the big boys like Kraken Mare and Ligeia Mare, were dynamic, active bodies. They rippled and stirred not just from the gentle gusts of wind, which on Titan would feel like a surprisingly soft, gentle exhale on your cheek due to the dense atmosphere and low gravity, but from powerful tides. These tides aren't caused by Titan's own moon. It doesn't have one, being a moon itself, but by the immense gravitational pull of its colossal parent, Saturn. Imagine standing on a shore where the tides are driven by a gas giant. It's a testament to the sheer scale and alien majesty of this distant world. Strange layers and stranger ice. Fast forward a decade from Huygens landing, and scientists on Earth were busy in their labs trying to unravel the mysteries Cassini's radar had revealed. They meticulously recreated Titan's frigid conditions, chilling methane-ethane mixtures down to a bone-chilling -183 degrees Celsius. What they discovered was utterly captivating. At these extreme temperatures, a methane-ethane mix doesn't just sit there. It can stratify into distinct layers, sometimes only a few meters thick, each with its own unique composition and density. Even more mind-bending, the bottom layer of these stratified lakes can become so incredibly dense that it actually squeezes out ethane ice. Yes, you heard that right. Ethane, which is a liquid at these temperatures, can form ice that then drifts upward. It's like reverse snow falling from the bottom of the lake towards the surface. Imagine trying to swim through liquid natural gas while chunks of hydrocarbon ice bob past your visor, defying all your earthbound expectations of buoyancy. It's an upside-down world where ice floats up from the depths. And the weirdness doesn't stop there. Nitrogen, which makes up the bulk of Titan's atmosphere, behaves very differently in these cryoliquids. It dissolves best in methane, So when a lake's top layer is rich in methane, it can hold a significant amount of dissolved atmospheric nitrogen, like a giant super cold soda. But when that methane begins to evaporate, perhaps on a relatively warm Titan afternoon, though still ridiculously cold by our standards, that dissolved nitrogen has nowhere to go. It burps out, creating fizzing clouds that, if scaled up, would look like champagne bubbles the size of houses. Cassini actually witnessed some of these dynamic events. Its instruments detected mysterious radar glints on the surface of some lakes, bright spots that would appear and vanish within weeks. Scientists with a touch of cosmic humor nicknamed them magic islands. The leading theory, born from these lab experiments and observations, is that these magic islands are precisely what we just described. Vast, temporary mats of organic foam burped up to the surface by those colossal nitrogen burps. These aren't solid land masses appearing and disappearing. They're transient phenomena, floating and dissipating, a testament to the incredibly active and dynamic chemistry happening just beneath Titan's hazy skies. It's a geological and chemical ballet playing out on a planetary scale, constantly reshaping the surface in ways we're only just beginning to understand. The organic factory. Above Titan's enigmatic lakes, high in the stratospheric reaches of its thick atmosphere, a silent but incredibly active organic factory is hard at work, powered by the sun's distant, weak ultraviolet rays. Here, sunlight relentlessly cracks apart the nitrogen and methane molecules that dominate Titan's atmosphere. This energetic bombardment isn't destructive in a simple way. It's a creative force, forging new, more complex compounds. Think of it as a cosmic chemical kitchen, where these broken molecular fragments recombine to create fascinating new ingredients like hydrogen cyanide, acetylene, and benzene. These newly formed compounds don't just float aimlessly. They begin to clump together, forming sticky, microscopic droplets. Slowly, imperceptibly, these droplets grow heavier and begin their long, gentle descent through the dense atmosphere, a constant, fine rain of organic particles. When they finally settle on the surface, they accumulate into a tarry orange frost known as tholin. Tholins are incredibly complex, carbon-rich macromolecules, and they're what give Titan its characteristic hazy orange glow. They're like the primordial ooze of this alien world, a constant source of complex organic material. When this tholin dust, this organic snow, finally lands in one of Titan's frigid lakes, the liquid hydrocarbons, especially ethane, which is a better solvent for smaller organic molecules, get to work. The ethane dissolves the smaller, more soluble components of the tholin, leaving behind a crunchier, more resilient scum of bigger, more complex polymers. Over eons, over thousands upon thousands of Titan years, this organic scum doesn't just sit there. It undergoes further transformations, folding itself into intricate bubble-like vesicles. These fascinating structures have been nicknamed azotosomes, a nod to their nitrogen-rich composition and their striking resemblance to the lipid membranes that encapsulate Earth's cells. Now, to be clear, these azotosomes are not alive. Not in the way we understand life anyway, but they are incredibly significant. They effectively trap tiny pockets of liquid, creating microenvironments where organic molecules can become concentrated, much like Earth's early cells concentrated ions within their nascent membranes. This concentration is a crucial step in the pathway to life, providing a localized space for chemistry to become more complex and efficient. The potential of these azotosomes isn't just theoretical. One groundbreaking experiment at NASA's Jet Propulsion Lab brought this alien chemistry to Earth. Researchers mimicked Titan's conditions, shaking a methane-ethane cocktail with tholin dust. The result? Hollow spherical structures that remarkably glowed under ultraviolet light. Nothing crawled out of them, thankfully, but the spheres lasted for months, stubbornly refusing to pop or dissolve. This demonstrated that these protocell-like structures are not only possible, but surprisingly robust under Titan-like conditions. If life were ever to arise on Titan, it might very well begin inside these wobbly hydrocarbon bubbles. Such life would be truly alien, operating on entirely different biochemical principles. Instead of breathing oxygen, it might respire hydrogen, a readily available gas in Titan's atmosphere. And instead of metabolizing glucose for energy, as we do, it might eat acetylene, another abundant organic molecule formed in Titan's atmosphere. It's a vision of life as we truly don't know it, a testament to the universe's boundless creativity. The missing ingredients. Here's the cosmic catch, the critical piece of the puzzle that has kept astrobiologists scratching their heads. For those fascinating azotosomes to truly transition from mere chemical curiosities to self-replicating entities, for them to copy information and evolve, they need a crucial ingredient: phosphorus. On Earth, phosphorus is abundant and essential, forming the backbone of DNA and RNA and playing a vital role in energy transfer. But on Titan, phosphorus is incredibly scarce. It's not a major component of the moon's icy crust or its atmosphere. So where could it come from? Meteorites are one possibility, occasionally delivering phosphorus-rich rocks from space. But Titan is far from the asteroid belt and significant impacts are rare. This led researchers to look deeper, literally, beneath Titan's surface. And what they found, or rather what radar reflections hinted at, was truly exciting. A hidden ocean of liquid water, buried some 50 to 100 kilometers beneath Titan's thick, icy shell. This isn't a hydrocarbon ocean, but a salty, warm water ocean, potentially rich in minerals, including phosphates. The question then becomes, if this subsurface ocean exists, how could its precious contents reach the surface lakes? The answer might lie in cryovolcanism. If that hidden ocean occasionally squeezes upward through cracks and fissures in the overlying ice shell, it could spew mineral-rich sludge onto the surface. This would be a cosmic delivery system, sprinkling phosphorus and other vital elements directly into the hydrocarbon lakes above. Cassini's observations provided tantalizing evidence for this. It spotted several craters and features that looked suspiciously like cryovolcanoes, ice volcanoes that, instead of erupting molten rock like their Earth counterparts, ooze briny, mineral-laden sludge or water-ammonia mixtures. One such striking feature, called Sotra Facula, rises a full kilometer above the surrounding plains. Its distinctive lobed flows, reminiscent of lava flows on Earth, visibly terminate at the shores of a small ethane lake. If those flows carry dissolved phosphate from the subsurface ocean, they could effectively fertilize the lake, turning it into a cosmic miracle grow, providing the missing ingredient for more complex chemistry and perhaps for life to begin its arduous journey. It's a beautiful thought. A hidden ocean, deep within an icy moon, feeding the surface lakes with the very elements needed to spark something truly extraordinary. The underground plumbing. Titan's lakes aren't just passive recipients of atmospheric rain. They're intimately connected to a complex, dynamic underground plumbing system that profoundly influences their composition and longevity. This subterranean network plays a crucial role in shaping the moon's surface and sustaining its unique hydrological cycle. One key player in this underground drama are methane clathrates, fascinating structures where water ice forms cage-like lattices, trapping methane molecules within them. Think of them as frozen cages of natural gas, sitting just below Titan's surface. These clathrates are stable under Titan's frigid conditions, but they're not entirely static. When seasonal warming nudges the surface temperature just a few degrees, these clathrates can destabilize, releasing their trapped methane. This methane and burps its way into the nearest lake, replenishing its liquid supply. Over vast stretches of geologic time, this continuous cycle of clathrate formation and destabilization is thought to be a primary mechanism for keeping Titan's atmosphere stocked with methane, even though sunlight constantly destroys it in the upper atmosphere. Without this underground reservoir, Titan's methane cycle would quickly run dry. But the plumbing goes even deeper. Scientists hypothesize the existence of deeper reservoirs, affectionately nicknamed alcanifers. These are subterranean conduits or aquifers that pipe liquid hydrocarbons directly from Titan's mantle to its crust, and eventually to the surface lakes. This deeper connection introduces another layer of complexity to the lake's chemistry. Lakes fed primarily by these alcanifers tend to be richer in heavier hydrocarbons like ethane and propane, because these denser liquids settle first in the underground plumbing system. In contrast, lakes that are predominantly fed by direct rainfall from the atmosphere tend to remain methane-rich, as methane is the primary component of Titan's rain. This difference in composition matters significantly for the potential for life. Ethane, it turns out, is a much better solvent for large organic molecules than methane. This means that an ethane-rich lake could potentially host a more diverse and complex array of prebiotic chemistry, providing a more fertile ground for the formation of those crucial azotosomes and other building blocks of life. Consider Ontario Lacus, a prominent lake in Titan's southern hemisphere. It's a prime example of this phenomenon, composed of about 75% ethane and only 20% methane, along with other trace hydrocarbons. This makes Ontario Lacus a giant, natural test tube for some truly weird and wonderful chemical reactions, a place where the conditions might be uniquely suited for the genesis of exotic biochemistry. The interplay between surface processes, clathrate dynamics, and deep subsurface alcanifers paints a picture of a moon far more geologically and chemically active than its icy exterior might suggest. Seasonal drama. Titan seasons are not like ours. Forget the fleeting 3-month cycles of Earth. A single Titan year stretches out for a staggering 29 Earth years. This means that each of Titan's 4 seasons endures for roughly 7 long Earth years, unfolding with a majestic, almost glacial pace. This extended time frame allows for dramatic planet-wide shifts in its climate and hydrology, turning the entire moon into a slow-motion spectacle of seasonal transformation. As summer gradually returns to Titan's northern hemisphere, a process that takes years, the increased, albeit still dim sunlight causes methane to evaporate from the surface and migrate polarward through the atmosphere. This atmospheric transport leads to significant changes in the northern lakes and seas. They begin to swell, gaining meters of liquid depth per year, a slow but relentless rise in their levels. This influx of liquid can carve new channels across the landscape, reshake existing river systems, and cause deltas to expand. But the drama isn't always gradual. Sometimes entire lake basins can drain overnight, seemingly disappearing in a blink of an eye. This isn't due to rapid evaporation. Rather, it's believed to be the result of an underground ice dam melting or an underground conduit opening up, allowing the liquid hydrocarbons to seep into the porous crust below. Cassini, during one of its many flybys, observed an astonishing example of this dynamic. It observed a 100-kilometer stretch of shoreline that had retreated a full 10 kilometers in just 6 months, an incredible rate of change on a planetary scale. The lake had either evaporated at an unprecedented rate or, more likely, simply seeped into the subsurface, vanishing from sight. Climate models, continually refined with Cassini's data, predict that by around 2040, the southern hemisphere of Titan will start gaining liquid again, mirroring the northern hemisphere's current state. This means that Ontario Lacus, the ethane-rich lake we discussed earlier, will likely begin to refill, and new rivers might even carve fresh paths across the southern plains. If you could live long enough, if you had the patience of a cosmic observer, you would witness a planetary-scale time-lapse, a slow-motion ballet of lakes blooming and withering across Titan's face, much like desert wildflowers after a rare, life-giving storm. It's a testament to the moon's active and ever-changing environment, a world where liquid landscapes are in a constant state of flux. Life as we don't know it. The ultimate question, the one that truly captivates our imagination, is this: could anything actually survive in this frigid hydrocarbon slurry? On Earth, we have an astonishing array of extremophiles, organisms that thrive in environments we once considered utterly inhospitable, from superheated volcanic vents to radiation-blasted deserts. These tenacious life forms demonstrate that life, given the slightest chemical gradient, will find a way to exploit it, to extract energy and propagate. This gives us hope for Titan. On Titan, the hypothetical microbe would be radically different from anything we know. Imagine a tiny organism encased in one of those azotosome membranes that could eat acetylene, one of the organic molecules formed in the atmosphere, and in doing so, exhale methane, releasing just enough energy to maintain and repair its delicate membrane. The hydrogen abundant in Titan's atmosphere could serve as the electron donor for this metabolic process, much like oxygen does for us. And the waste product, more methane, would simply slip back into the lake, closing the loop in a beautifully self-sustaining alien ecosystem. Of course, such organisms would be incredibly sluggish. Chemical reactions, the very engine of life, run about 6 times slower at Titan's brutal minus 180 degrees Celsius temperatures than they do at Earth's more temperate conditions. But slow doesn't mean impossible. A single cell division for a titanium microbe might take a century or even longer. Yet Titan has billions of years to spare, an immense stretch of time during which even the slowest evolutionary processes could unfold. The universe, after all, is not in a hurry. The real test for this hypothetical titanium life, and a key focus for future missions, is reproduction. Can these azotosomes copy their contents? Can they replicate before the harsh UV radiation from the sun or other environmental stressors shred them apart? This is where the scarce phosphorus element comes back into play. Lab simulations have shown that if phosphorus, even in tiny amounts, shows up even once every 1,000 years, perhaps delivered by a cryovolcanic eruption or a rare meteorite, then the answer is a resounding yes. The odds, while long, are not insurmountable. The possibility of life, even if it's a slow-motion, hydrocarbon-based life, existing in this alien environment, is a powerful testament to life's adaptability and the universe's infinite potential for creative chemistry. The Dragonfly Revolution. Right now, as you read this, a revolutionary piece of machinery is being meticulously bolted together in a pristine clean room in Maryland. Its name is Dragonfly, and it represents our boldest, most ambitious attempt yet to truly understand Titan's secrets. Scheduled to launch in 2027 and make its dramatic landing in 2034, Dragonfly isn't a rover, nor is it a lander. It's a nuclear-powered octocopter, a drone the size of a golf cart, designed to fly, not roll, across Titan's alien landscapes. Dragonfly's mission is utterly unique. Every Titan day, that's a full 16 Earth days, it will perform a series of hops, flying 5 to 10 kilometers at a time. This unprecedented mobility will allow it to explore a vast and diverse range of environments. As it flies, it will sample the soil, sniff the air with its onboard mass spectrometer, analyzing the complex organic chemistry of Titan's atmosphere and surface. And critically, it will drop a small drill into lake beds and other fascinating geological features, gathering samples for detailed analysis. Its first prime target is Celt Crater, a 90-kilometer wide impact basin that scientists believe once held a lake. The Dragonfly team is eager to measure the precise ratio of ethane to methane in the sediments there, to hunt for tholin-rich deposits, those tarry organic frosts we discussed, and crucially, to check if any phosphorus has seeped to the surface, providing that vital ingredient for potential biochemistry. Over its baseline mission, which is planned for 2.7 Earth years, Dragonfly is expected to log an astonishing 175 kilometers of flight distance. To put that into perspective, that's more than every Mars rover combined has traversed on the Red Planet. Its ability to cover such vast distances and access varied terrain is a game changer. If, during its journey, Dragonfly spots azotosome-like vesicles, those protocell structures, or detects a suspicious excess of hydrogen, a potential byproduct of exotic metabolism, then the headlines will truly write themselves. It won't just be a scientific discovery. It will be a profound moment for humanity, a potential answer to the age-old question, are we alone? Dragonfly isn't just a mission, it's a revolution in planetary exploration, a testament to human ingenuity and our insatiable curiosity. Why it matters. So why does any of this truly matter? Why pour billions of dollars and decades of effort into studying a moon over 1 billion kilometers away? Because Titan teaches us a profound and humbling lesson. Life doesn't need Earth's playbook. Our planet's specific conditions, liquid water, oxygen atmosphere, temperate climate, are not necessarily universal requirements for biology. What Titan suggests is that life, in its most fundamental sense, might only need 3 things: energy, organic molecules, and time. Nothing more, nothing less. If chemistry can, against all odds, bootstrap itself into Darwinian evolution within a frigid methane slurry, then the implications are staggering. It means life might truly be everywhere. It could be lurking in the ethane clouds of brown dwarfs, those failed stars that glow faintly in the cosmic darkness. It might be thriving in the hydrocarbon haze of exoplanets orbiting distant suns, or even in the frozen lakes on rogue worlds, drifting through the inky blackness between stars, unbound by any stellar parent. Each discovery on Titan, each new piece of the puzzle, chips away at our cosmic loneliness, nudging us closer to the realization that we might be part of a much larger, more diverse biological tapestry. Even if, ultimately, Titan proves to be sterile, devoid of any active biology, its importance remains immense. Its lakes and atmosphere constitute a natural, planet-sized laboratory for prebiotic chemistry. Earth, in its early, tumultuous history, probably went through a similar tarry phase, a period when complex organic molecules were forming and interacting, laying the groundwork for the first true cells. On Titan, we get to watch that experiment unfold in slow motion, preserved at cryogenic temperatures, offering us a pristine window into the very origins of life. It's a chance to see how the universe got started, how it built the fundamental components of biology right before our eyes. That, in itself, is an invaluable gift. Mid-roll CTA. If you're as captivated as I am by the thought of Dragonfly sending back its first pictures from this incredible world, then make sure you hit that subscribe button and ring the bell. Titan seasons turn slowly, but news breaks fast around here, and you won't want to miss a single update from the forefront of space exploration. What we still don't know. Even with all the incredible data from Cassini and the promise of Dragonfly, Titan remains a world teeming with unanswered questions, each one more tantalizing than the last. That's the addictive nature of planetary science, isn't it? Every answer spawns three new, deeper questions. For instance, those magic islands. Do they genuinely migrate across the lakes with the prevailing winds, shifting like ephemeral rafts of foam? Or do they simply sink and dissipate when the nitrogen stops fizzing, only to reappear elsewhere? What's their true lifespan? And what about those methane clathrate burps from beneath the surface? Are they powerful enough, when they destabilize and release their gas, to trigger tsunamis across the vast expanse of Kraken Mare, sending hydrocarbon waves crashing onto distant shores? How much phosphorus is truly locked away in Titan's deep, icy mantle, patiently waiting for a cryovolcanic eruption to bring it to the surface? And when will the next one occur? Will dragonflies drill, designed to penetrate the lake beds, hit an unexpected layer of pure ethane ice that's so hard and brittle it shatters the bit, presenting a whole new challenge for the mission? We still don't fully understand the precise mechanisms of lake formation in different regions. Why are some lakes fed by rain and methane, while others are dominated by ethane from subsurface sources? Do these different feeding mechanisms lead to distinct chemical environments that could favor different types of prebiotic chemistry? And what about the long-term stability of these systems? Are the alkanifers a consistent, steady supply, or do they ebb and flow over geological timescales? The mysteries are endless, and that's precisely why we keep looking, keep exploring, and keep asking questions. The long view. Dragonfly is just the beginning. Its mission is to scout, to sample, to tell us where to look next. And if it finds compelling evidence of complex organic chemistry or even potential biosignatures, the next step might be truly audacious. Someday, perhaps in our lifetimes, we might send a submarine to Kraken Mare itself. NASA has already floated a design for such a mission. A sleek 1,000-kilogram torpedo-shaped probe equipped with a paddle wheel for propulsion and a periscope mass designed to peek above the liquid surface, sending data and images back to Earth. This robotic submariner would cruise through Kraken Mare's frigid depths for 90 days, meticulously mapping the lakebed topography, searching for hydrothermal vents, if they exist, and most importantly, sniffing for those elusive hydrogen-breathing microbes we've hypothesized. The proposed launch window for such an incredible mission? As early as 2047. The estimated cost? A cool $2 billion. The risks? Enormous, both technically and financially. But the potential reward? The first definitive detection of alien life, a discovery that would fundamentally alter humanity's perception of its place in the cosmos. Even if the Titan submarine never leaves the drawing board, Dragonfly will have paved the way. It will prove unequivocally that sustained flight is not only possible, but practical, in an atmosphere 4 times denser than Earth's and with only 1% of our planet's gravity. This technological leap will unlock entirely new possibilities for exploring other worlds with thick atmospheres from Venus to gas giant moons. It's a stepping stone, a crucial proof of concept that expands our toolkit for understanding the universe. The long view of Titan exploration isn't just about one moon. It's about pushing the boundaries of what's possible, about daring to dream of life beyond Earth, and about building the tools to find it. Closing thought. Next time you pour yourself a cool, refreshing glass of water, take a moment, pause, and remember this. Somewhere, a staggering 1.2 billion kilometers away, a different kind of rain is falling. Methane, not water, is condensing from thick, hazy clouds and drizzling into a lake so cold it would instantly shatter your glass, freezing it solid in a microsecond. Yet in that same impossibly frigid lake, amidst the alien chaos and non-ideal mixtures, the precursors of biology might be stirring, slowly, patiently, waiting for their moment. Titan's legs aren't just astronomical curiosities. They are, in a profound sense, mirrors, showing us how incredibly adaptable, how unimaginably creative chemistry can be. Whether they ultimately hold floating icebergs of ethane, fizzing nitrogen bubbles the size of houses, or even those elusive microbes breathing hydrogen, they whisper the same powerful message. The universe is stranger, more diverse, and far more creative than we ever dared to imagine. It's a message that urges us to keep looking up, to keep asking questions, and to keep pushing the boundaries of our knowledge. And who knows? Maybe one day humanity will venture far enough to taste the methane rain for ourselves, to truly immerse ourselves in the wonders of Titan. Like this deep dive into alien seas and the mysteries of Titan? Then smash that like button, share this video with a friend who lives for weird worlds, and check out our playlist on the outer solar system for more mind-bending tours of our cosmic neighborhood. Until next time, stay curious, stay brave, and never stop wondering what's really hiding just beneath the surface.